As I said, our PowerPoint presentation is about introducing polymerization reactors and exploring the different types of reactors available, along with general design principles. It's important to understand why we need polymerization reactors in our processes. These reactors actually play a vital role in producing a diverse range of polymers that are used in everyday products. They are designed to facilitate the chemical reaction that forms polymers from monomers, to select the most appropriate reactor for specific polymerization processes. Of course, it's crucial to understand the different types of reactors and their unique characteristics. In polymerization, there are three types of reactors. The first one is batch reactors, second one is continuous stirred tank reactors or CSTRs, and the third one is plug flow reactors or PFRs. Batch reactors are versatile and commonly used for small scale and small volume production and experiments, while CSTRs are well suited for high volume production, and they maintain a consistent reaction environment and efficiently produce polymers with uniform properties. PFRs are often used for producing polymers with specific characteristics, as they are efficient in mass and heat transfer and suitable for reactions with narrow residence time requirements. Batch reactors are an interesting topic, and there are different types of batch reactors that can be used for polymerization. One example is stirred tank reactors, which have a tank that contains the reaction mixture and the mixing device to ensure proper mixing and heat transfer throughout the process. Another kind of batch reactor that we have is a tubular reactor. Tubular reactors are long, hollow tubes through which the reactants flow, and these reactors offer advantages such as high heat transfer rates and better control over residence time, and we will talk about their advantages later. As you can see, tubular reactors offer several advantages, including efficient heat transfer, and the second one is continuous operation. Efficient heat transfer is facilitated by the use of these reactors, and they also provide precise temperature control during polymerization. Additionally, their capability of continuous operation makes them ideal for large-scale production with consistent quality. Another kind of batch reactor that we have is a semi-batch reactor. The semi-batch reactor is a versatile type of reactor that combines features of both batch and continuous reactors, and it allows for the controlled addition of reactants or removal of products during the reaction process, and this flexibility makes it suitable for complex reactions and production of high-value products. When designing stirred tank reactors, it is common to approximate or model their behavior using an ideal CSTR. This model assumes that perfect mixing occurs within the reactor and reagent is instantaneously and uniformly mixed upon entry. As a result, the output composition identical to the composition of the material inside the reactor, which is determined by, for example, the residence time and reaction rate. The CSTR is considered the ideal limit of complete mixing in reactor design, while a PFR represents the opposite end of the spectrum. In reality, if you want to say, most reactors that we have fall somewhere between the mixing limits of an ideal CSTR and PFR, sorry. When it comes to discussing the pros and cons of a CSDR, we can highlight some of its advantages. For instance, CSDRs are efficient in managing and processing large volumes of materials, resulting in consistent production and uniform polymer properties. However, there are a few drawbacks to consider. One of them is this, that CSDRs may have longer residence times, which could lead to unwanted side reactions and reduced selectivity. Plug flow reactors or PFRs. Sometimes referred to as a continuous tubular reactor or a piston flow reactor, is a model used to explain chemical reactions in cylindrical continuous flowing systems. By using the PFR model, we are able to predict the behavior of chemical reactors with the design and estimate key factor variables such as the reactor dimensions, for example. Plug flow reactors or PFRs offer several advantages, including efficient mass transfer and precise control over the polymerization process. The efficient mass transfer is achieved through excellent mass transfer provided by PFR, resulting in more uniform product quality. Additionally, we can say that precise control over the polymerization process and the properties of the produced polymer is possible with PFRs. Fluidized bed reactors or FBRs, that you can see their picture here. We can say that a fluidized bed reactor, which we call FBR, is a type of reactor device that can carry out various multi-phase chemical reactions. In this type of reactor, we can say that a fluid that can be gas or liquid is passed through a solid granular material, usually a catalyst, at high enough speeds to suspend the solid and cause it to behave like it were fluid, for example. And this process, that we know it as fluidization, impairs many important advantages of an FBR. As a result, I can say that FBRs is usually used for many industrial applications. Fluidized bed reactors can offer different advantages for us, like high heat and mass transfer and limited reactor volume. About the first one, we can say that fluidized bed reactors offer efficient heat and mass transfer, ensuring uniform polymerization, and the second one, that is limited reactor volume, we can say that they require less space compared to other reactors, so it makes them suitable for facilities with space constraints. To compare the different types of reactors, we can analyze their production volume, operational cost, and product quality. Each reactor type has varying capabilities for handling production volumes, which affects overall efficiency. Different reactor types also vary in their operational costs, considering factors such as energy consumption or maintenance requirements. In addition, the suitability of a reactor type for maintaining consistent product quality, of course, is a crucial consideration. That you can see them here. When selecting a reactor, it is important to consider various factors. One of the key factors is the reaction characteristics, including the specific requirements of the polymerization reactions, such as residence time and temperature sensitivity, for example. Another crucial factor is the cost and energy efficiency. Evaluating the operational cost and energy efficiency is necessary for sustainable production. In conclusion, I can say that selecting the right polymerization reactor entails a meticulous assessment of several factors. These factors include reaction features, operating expenses, and production needs, and it's essential to recognize the distinct advantages and limitations of each reactor type to achieve optimal polymer production that is efficient of a high quality. The end.